Hi, my name is Brooke Hollingshead, and this is a recursive sequence demonstration for Math 500. So our sequence is a sub n plus 1 equals 1 over 1 plus 1 over the square root of whatever our last term in our sequence was, or a sub n. We're also given that our first term in our sequence is 1. So the first thing we're going to do is find the first several terms. So we were already told that a sub 1 is 1. A sub 2, we use the formula that we're given, 1 over 1 plus 1 over square root of whatever our last term was, so that was 1. This gives us 1 over essentially 1 plus 1 or 1 over 2. A sub 3, we do the same thing then, 1 over 1 plus 1 over square root of 1/2. And the math starts getting kind of crazy on these, so I'm going to put them into decimals. So I'm actually going to go back and write this one as a decimal too then, 0.5. 0.4142. When we do this, 1 over 1 plus 1 over square root of 0.4142, we get 0.3916. And if we go one more term, 0.3849. This is actually going to start converging to a limit that we'll see later that is about 0.38197. Okay, so the next thing we're going to do is talk about the monotone sequence theorem. If a sequence is bounded, we have a bound on the top, we have a bound on the bottom for this one, and it's monotonic, increasing or decreasing. This one is going to end up being decreasing. Then it also converges to some limit. So we're going to prove that ours has a limit by showing first that it's bounded and decreasing, and then we're going to look at what our limit is. So decreasing means whatever my term is greater than the next term. The next term should be getting smaller and smaller and smaller. So if I have a sub n is greater than, my formula says that the next term is 1 over 1 plus 1 over square root of a sub n. I'm going to take this denominator and multiply both sides. So I have a sub n plus a sub n over square root of a sub n greater than 1. This can be rewritten as just square root of a sub n when you multiply the top and the bottom by the same denominator. Okay, so the way that I know that this is true is that our first a sub n was actually 1, and this must be a positive number. So if we start with our first one, and we're adding some kind of a positive number, our numbers should only be getting bigger on this side. They should always be greater than 1, because we started with 1 anyway. So 1 plus any kind of positive number is going to be greater than 1. And then the next one, same thing. We're going to be greater than 1 because we're starting with 1 the whole time. So we know this is true. We're decreasing because we ended up with a true statement here. So now we need to show that we're bounded. We're actually going to be bounded on the lower limit, and I'll prove this in just a minute, by 3 minus square root of 5 over 2. This is less than some a sub k term, actually all the a terms in our sequence, but we'll show this. And we're bounded on the top by 1. Because we're decreasing, because we started at 1, 1 is our topmost point. Okay, so if I take both sides, this was actually, I'm going to write that as a decimal because it makes the math much easier to work with here, 0.38197. All right, so I'm going to take the square root of everything. Square root of 1 is 1. Square root of 0.38197 is 0.61803. Okay, then I'm going to do 1 over what our term was. 1 over 1 is still 1. 1 over this is actually interesting, 1.61803. Then I'm going to add a 1 to it. 1 plus. I'm building essentially what my sequence formula is. Add a 1 there, add a 1 there. Okay, and then the last thing I need to do is put all of that in the denominator with a 1 on top. 1 over 2. And if I do that on this side, I end up with 0.38197. Okay, this is back to the beginning, 3 minus square root of 5 over 2. This is the same as my formula, a sub n plus 1. This is actually less than 1, so that's less than or equal to 1. My whole sequence is less than or equal to 1 on the top bound, bottom bound, 3 minus square root of 5 over 2. Now that I'm decreasing and bounded, I know I have a limit. This means that the limit as n approaches infinity exists, and it's the same for each term. So the limit of a sub n and the limit of a sub n plus 1 are both L. So I'm just going to replace everything in my formula with L. 1 plus 1 over square root of L. Multiply both sides by this denominator. L plus L over square root L equals 1. This can be rewritten as square root of L. I'm going to subtract L from both sides. I'm going to square both sides. L equals 1 minus 2L plus L squared. Subtract L. I end up with a quadratic formula that I have to use, a quadratic equation I have to use a quadratic formula to solve. This tells me eventually 3 plus or minus square root of 5 over 2. Well, 3 plus square root of 5 over 2 is above my upper limit, so I know that that one will not work. So my limit has to be 3 minus square root of 5 over 2. So the sequence converges to that limit.